Okay, okay, recording started. Hi guys, so I'm back. Sorry about that. There was a technical problem. Actually, my electricity went off, but it has come back. So I am back. Perfect. So, do you guys hear me? You can hear me? Hello? Yeah, very good. Yeah, I think my connection seems to be okay now. Wonderful. Yes. Very good. All right. Sorry about the delay. There was this undesirable issues came up. I don't know why. Actually, it's not technical even. Just there was electricity failure in the entire building, and they put everything back now. So looks like it's fine. And it came back, and then it went off again. Now came back. So again, it comes back, goes off. That's because of the electricity issues. Anyhow, so without much talking, so today we are nearing the end. As you know, we have only one more lab left, I suppose, right? So one or two at the most. uh, so today, obviously, you are going to be doing a very interesting, today meaning tomorrow, you will be doing a very interesting lab. And as the advanced course advances, you get even more advanced lab. So for example, today's lab, as you know, it's a synthesis of a sulfur drug. So that should be quite exciting for you, that you can synthesize. uh, when is it going to be the final? It's in the syllabus, Anthony, it's in the syllabus. I'm forgetting the exact date. I can check. I think it is indicated is Franklin answered the December 13th. I believe that is correct. I just did not want to tell you without being sure. It is in the syllabus and it will be as such. So December 13th sounds to be correct, yes, but you can double check. Uh, all right, so without much ado, so let's get started. So you'll be synthesizing a sulfur drug. So first time you're synthesizing a drug should be quite exciting. And the sulfur drugs have been in use for a very long time, almost 80 years now. The particular sulfur drug you are going to be using is sulfanilamide. You may have heard about this. Sulfanilamide is a compound that is actually an antibacterial uh, chemical or antibacterial drug. So let me start writing. Synthesis. And also I'm writing on one note. I don't like this app very much. It's not really powerful, but this one, at least it will not kick me out like as it happened last time, as you recall. Synthesis of sulfanilamide. And you will be doing started with aniline. Aniline compound, you have known this before. The benzene ring with an amino group on it is called aniline, right? That's aniline. So from aniline, after multiple steps, you are going to be making sulfanilamide, which is going to have on its para position this group, NH2. So since you have all completed 263, it will be quite easy to follow all these steps. It's a combination of 2 or 3 different types of reactions that you have learned in the past. That involves, for example, and as you know, each chemical reaction is like a chemical tool from a toolbox that you will be utilizing one after another. So let me list those tools, meaning the chemical reaction types that you are going to be doing in this reaction. One reaction, for example, is electrophilic aromatic substitution. You are familiar with this electrophilic aromatic substitution, if I write in a general term. Is that you react with an electrophile, and there are various types of electrophiles you have used. You did chlorination, nitration, sulfonation, etc., etc., and you get an electrophilic substitution, hydrogen is replaced by and electrophile. So that reaction that you have learned is electrophilic aromatic substitution. So you might as well want to quickly check what you learned there. And followed by another reaction you're going to be doing is nucleophilic acyl substitution. This reaction is based on the carboxylic acid derivative. Let's imagine one of the derivatives you had used, for example, acid chloride, and you had known few other derivatives, acid anhydride or ester react in the similar manner. In this case, reaction is with a nucleophile, and how the nucleophile reacts is nucleophile attacks the carbonyl carbon. Very lengthy discussion is done in the lecture class because it's like 3 weeks, so 6-7 hours of lecture. So you have learned this. I cannot possibly do the whole thing. Still, I am showing you the mechanism for quick refreshing your mind. So it becomes O minus, Cl is there. Here the nucleophile attaches to the carbonyl carbon. In a nucleophilic acid substitution, carbonyl bond reforms and the halogen leaves, or any other leaving group that leaves. In an acid anhydride, you will have a carboxylate leaving group. In an ester, you will have an alkoxy leaving group or alkoxide, right? So the bottom line is, in the end, you get a acyl substitution. The leaving group is gone, carbonyl is reformed, nucleophile stays, right? That is the reaction you learned. Is called nucleophilic acyl substitution. So you're going to be doing both actually in this particular reaction that you will be doing tomorrow. Another interesting additional reaction you have learned in the same chapter of aromatic reactions was that some of the functional group you can change one into another. And there are some restrictions, there are some limitations. We'll use some of those in this one single lab. So that's why it is a really, really advanced lab in that sense. So for example, an additional tool you have learned, which is a very simple tool, is that benzene you can do nitration, which is your electrophilic aromatic substitution. Nitric acid and sulfuric acid is the reagent, and that forms a nitrobenzene. This reaction I believe you have done in organic 1. That makes nitrobenzene. Followed by, if you reduce the nitro group using zinc and hydrochloric acid, and zinc can be tin or lead, but zinc is most common, that will change this NO2 into NH2. And that, as you can see, that is aniline. So starting from benzene, in 2 steps, you can get aniline. Now, you have also learned in that same chapter is this effect of this substituent group on the ring. So for example, NH2 group, amino group, is the strongest activator. You remember that? Strongest activator. So some of the things you learned before we are going to be put into practice. So what was the problem with the strongest activator? It really makes the ring extremely reactive, which is true, but it can also cause some unusual problem, undesirable problem. It is too good for some purposes, which is if you want to do certain electrophilic aromatic substitution, whether it's chlorination, bromination, or sulfonation, any of this, halogenation you do with X2 and FeCl, sorry, Epi, I should write X, Epi X3, remember that should go do halogenation. But because amino group is the strongest activator, it halogenates all 3 positions at once. So that was a big problem. Likewise, on aniline, if you are to do sulfonation, even sulfonation, which is fuming sulfuric acid, H2SO4, that will sulfonate also all 3 positions. So again, SO3 in both ortho positions and the para position. So that is a problem. And there was a solution to this problem. Those who are in my class, you have learned this. And the problem is we can change this strongest activator into a moderate activator, right? This one, if I write it here, this is the strongest activator. So that is why reaction occurs everywhere. So we can change it to a moderate activator by doing another reaction. What reaction was that? Anyone remembers? If not, that's okay. Reaction was with acetic anhydride. Do you recall this guy? It's called acetic anhydride. You have used many times. Acetic anhydride. So this part of the reaction is nucleophilic acyl substitution. Nucleophile is the nitrogen of the aniline that attacks the carbonyl carbon and has a leaving group, which is a carboxylate part that goes away, result of which you get a nucleophilic acyl substitution on the carbonyl group, nucleophile being NH2, makes it NHCOCH3. Okay, so that is a nucleophilic acyl substitution on acetic anhydride. Reactant or reagent is aniline. So, by the way, you will be actually starting from aniline. Your starting point is not going to be benzene. Just to know, you start from here. How do I write? I don't have too many colors of things. You start from here. From here meaning this, from aniline. So you will react with acetic anhydride and you change it to acetanilide. This guy is called acetanilide. Acetanilide. What is the advantage of that? When you make it acetanilide, now if you do any reaction, then it will go only one place, not all three places, because NHCOCH3 is no longer the strongest activator. It has turned into a moderate activator. So now it is a moderate activator. Moderate activator, if I write that. Moderate activator. So all the intellectual truths you learned are going to be utilized in this lab. So therefore, now if we are going to do sulfonation, for example, then it is not going to sulfonate everywhere. It will going to do the reaction at the para position. Para position is the major product. You get minor product as ortho, but we are going to be talking about the major product. So you get sulfonation there. And then if you do a base hydrolysis, H2O and sodium hydroxide, for example, that reaction is just hydrolysis, then our NHCOCH3 comes back to NH2 because that part is an amide. Amide hydrolysis makes it amine, so you get NH2 back. So you see, by converting NH2 into NHCOCH3, we deactivated the group, okay? And by doing so, we are able to selectively have substitution reaction on one position. So this is another tool that is going to be in use in your lab that you are going to be doing, okay? So now let me show you the whole thing. These are the different tools I'm talking about, right? These are conceptual and chemical reaction tools: electrophilic aromatic substitution, nucleophilic acyl substitution, and where you can make aniline from benzene. And we are showing why aniline itself would be too reactive and therefore you cannot do substitution on one position, but we can do by changing to acetanilide and then do substitution reaction followed by hydrolysis. So these are very clever tools for use. So that is, all these tools are going to be used into one experiment, which is your reaction. So let me show you the whole story, whole package, because you will be starting from aniline. you start from aniline. And as I had just shown you, you react with acetic anhydride and you turn into acetanilide. NHCOCH3. I think I have written the names already. So you start with aniline, becomes acetanilide, followed by you will be doing this time the reaction you're doing, it's kind of a sulfonation, but the reagent is chlorosulfonic acid, which is HOSO2Cl. That will have a electrophile. SO2Cl is the electrophile. That is going to be electrophile coming from that, which as an electrophile will undergo electrophilic aromatic substitution on the benzene ring. And because we have now a moderate activator, product substitution will occur at the para position. So that means you get NHCOCH3 stays, COCH3, and substitution is occurring at the para position. This is the group you are getting at the para position, which then you do another level of nucleophilic acyl substitution type reaction, except that it is not carbon related acyl, it is sulfonyl. Carbon oxygen double bond and sulfur oxygen double bond will react in the same manner. I had shown this tool few minutes ago. Here, take a look. Nucleophilic acyl substitution. Nucleophile attaches the carbonyl group. Carbonyl O becomes O minus. It reforms the carbonyl. Leaving group leaves. So same reaction can occur on a sulfonyl group. Instead of a carbon oxygen double bond, it would be on sulfur oxygen double bond. And that is what you see in this structure, sulfur oxygen double bond. Okay, and this you react with excess ammonia. I'm writing ammonia, but put emphasis on excess. Okay? So using excess ammonia, basically your ammonia is the nucleophile. If I think I have enough time to show that step, imagine you are doing nucleophilic acid substitution, meaning it attacks the sulfur double bond breaks, very similar manner as carbon oxygen double bond, same style reaction. So I'm leaving this as such. NHCOCH3, sulfur O is becoming O minus, this double bond stays. Here is your chlorine, and new group that has come is NH3, but NH3 neutral itself became plus because it gave electron, lost negative charge became positive. In other words, nitrogen has 4 covalent bonds, positive. This is something you have learned in organic to many reactions. I'll give you starting with organic 1. So as I said, this reaction is very much like your acyl substitution type, which means this sulfonyl group reforms, and this time your leaving group is the chlorine, because we know chlorine is a good leaving group. So it can be kicked out easily, it will leave easily. So as it leaves, what's happening from there is this part. NHCOCH3 stays as such, and your sulfonyl group backs here, and you have this new group is NH3. Of course, if you are writing NH3, that is still plus, but you can deprotonate it easily. In this case, just instead of thinking simple deprotonation as such, we can imagine the whole structure you are hydrolyzing, because we can also hydrolyze this NHCOCH3. Remember the tool I had just shown you? You can convert it back to NH2 by doing a base hydrolysis. So if you do the same base hydrolysis, so you see I am putting emphasis on water first. But it is, of course, base hydrolysis, you will have sodium hydroxide. Hydrolysis means water splitting, you must have water. So just not sodium hydroxide, but plenty of water. So if you do hydrolysis, what do you get? Your acetanilide group turns into NH2, like the reaction tool I showed earlier. And this part is going to get deprotonated. Nitrogen has this extra proton that will be deprotonated, turns into NH2. Guess what? That is your sulfanilamide. So that is the antibacterial compound sulfanilamide. It is used heavily during World War II to treat the wounded soldiers in Europe. Uh, that is the time it was used a lot. But there has been much greater improvements. So honestly, this is not used much anymore because there are much better and safer alternatives in use. I was reading some literature. It shows actually it is still used to as an antibacterial cream for females. I don't know why, and that is being still permitted. But literature shows that it is doctors often prescribe that as an antibacterial agent for genital area, etc. So that is the experiment you are doing. So as a sulfur drug, there are much better alternative to this, but this is a method to show how you can synthesize a sulfur drug, which is your sulfanilamide. So it's antibacterial agent, can be used in a cream as an antibacterial agent, itching and etc. Antibacterial agent. All right. So that is the experiment you are doing. The product is a solid product. You will be able to isolate very easily, and its melting point is 165 degrees Celsius. Uh, so you will be checking its purity. Check purity with TLC and also take NMR. So NMR should be easy because the substitutions are para to each other. So benzene ring protons are divided only into two groups in the region between 6.5 and 8. And NH2 group, you are going to see a peak which can be variable depending on the concentration. It can range anywhere 2 or 3 in that region. Okay, 2, 3 or 3.5, etc. But obviously that is going to be a singlet. And other than that, you are going to have peak between 6.5 and 8, which is the benzene ring aromatic signal. Other than that, there is nothing. So that should be quite good NMR. Now you have done some NMR. Tell me, give me some feedback. How did the NMR come out to be? I have seen some NMR last year that was not satisfactory to me, but how are you getting this time? Please tell me. And secondly, do you have any questions about the experiment? Anyone? 2 weeks ago, NMR was messed up, not satisfactory anymore. Yes, I agree with you. I have seen that. I was not very encouraged by that at all. Anyhow, I'll have a talk with the chair. But the thing is, this is just to have you get physically touch an NMR machine. Oh, really? There was even pig where it was not supposed to be. Yeah. Yeah, I have seen the last year the resolution was horrible and there was too much noise. It was really, really horrible to me. Um, and how much betterment can be done on this? I'm not sure. I'll ask Kunga, but he is going to teach me that, oh, this is the best we can get. So that's not going to help much either. All right. Yeah, that's okay. If chloroform is not shown, that doesn't hurt at all much because you want to see your other peaks. That is going to be more important. That patient is made in such a way that it is automatically calibrated uh, with TMS being zero, so that number is set automatically. In other words, it is based on this chloroform, and meaning all your other delta values are going to be accurate. You will not be even seeing it TMS peak at all, most probably. Have you been taken to the other NMR machine room where Dr. Prodan shows 400 or 300 megahertz NMR? You have not. Okay. So I will make a mention and see if that can be arranged. I hope those guys are cooperative. If they are, that would be possible. And Dr. Pradhan is very cooperative. He is a very nice guy. Just TAs will have to talk with them and make an appointment and set a time to be able to see that. Um, all right, guys. Uh, all right. Yeah, let's see how it goes exactly. So other than that, do you have any other questions? Any questions about today's lab or today's discussion wise? All right. You're welcome. So, all right. So I'll see you tomorrow then, and then you are going to have a turkey break, Thanksgiving break. So enjoy the Thanksgiving break. Although you are not going to be missing lab, which is good in a sense. So next week we will have lab as usual. Things will work fine. Perfect. All right. So happy Thanksgiving to everyone. As you know, the lecture is recorded, so you'll be able to check as you want. Okay. All right. Thank you. Thank you, guys. All right. So I'll see you next week. Have a nice lab.